In the last video you just saw a quick explanation of what a group is. And before I have you do any problems relating to groups and proving that things are groups or showing that you think things are groups, I just wanted to go through one slowly and give you an example. So, to prove something is a group, we need to have all of these criterion. We have that the group has elements in it, the group is non-empty, it has an operation, that operation is closed. So say this is the operation, that operation is closed, and you learned what closure meant earlier. That operation has inverses, and we'll talk about what that means. That operation has an identity, and that operation is associative. Okay. And so we're going to use the clock group for the group a 4-hour clock, and a 4-hour clock would look something like this. We have the 0 hour, we have a 1, a 2, and a 3, and you can imagine that if you're at the 1 hour and you add, I don't know, 4 hours to that, or let's keep it in the group, let's add 2 hours to that, well, that's 1, 2. So the 1, 2 spot should be 3. And if I go over 1 and down 2, the 1, 2 spot here, the 1, 2 spot is 3. So this preset table, this table that I have set up, describes the 4-hour clock. So let's start proving, let's start showing that these characteristics exist. So part 1, I'll do this in green. The set contains elements. Well, clearly the set contains elements because 0, 0 is 0, 1, 1 is 2, 1, 2 is 3. We have all of these values. These values are the entries. They are the elements. So we have elements. Our group is not empty. That's an easy one. The other part is that we have an operation. We clearly have an operation. We have the plus sign, so that one's done. Now, a slightly more confusing one is we need to prove that it's closed. So this is our operation, our plus sign. And we need to show that this is closed. And when you have the Cayley table describing it, when you have this table written out, it's clear to see whether it's closed or not, because all you need to make sure is all of these elements are the only elements in the table. For example, we have a closed set right now because we only have 0, 1, 2, and 3. An example of a non-closed set would be if this 0 were a 4. If we had a 4 there, then we would have our set of elements such that 2 plus sign 2, if we're using our operation 2, operation 2 would equal 4, and that would be a problem because 4 is not one of the elements here, and it's not one of the elements here. So that would not be closed, but in fact, we do have a closed set because I can erase all of that, and we have a 0 there, which is part of our elements. So we can say without a doubt this is closed under our operation. Now the next part is inverses. Let's see what inverses do. Inverses bring us to the identity element. So for example, if I have the number 1, well, what's 1's additive inverse? The additive inverse of 1 is negative 1, because 1 plus negative 1 is 0. 0 is our additive identity. 6 plus negative 6 is equal to 0, so those two are additive inverses. If you're thinking in the terms of multiplication, well, 2 times what equals the multiplicative identity, which is just 1. 2 times 1/2 is equal to 1. So 2 and 1/2 are multiplicative inverses. So in fact, in our list here, I'll leave that for now. In our list here, I'm going to skip inverses, and I'm going to start with identities, because knowing the identity will help us show that there are inverses. So let's start with identities. What's identity mean? Well, the identity, the additive identity is 0, which means a number like 5 plus 0 equals 5. Or 55 plus 0 equals 55. Any number plus 0 equals itself. and that's because 0 is our additive identity. And multiplicative, 3 times 1, we know 1 is our multiplicative identity because 3 times 1 equals 3. 472 times 1 equals 472. Our identity just keeps our operation the same, keeps our element the same. So in what case here would, for example, let's start with 0. 0 plus sign, some element here equals 0. Which one? Well, 0 plus sign 0 equals 0, because we have it right here. And 1 plus sign 0 equals 1. We have that right here. And 2 plus sign 0 equals 2, and so on. So it looks to me like, and we can see that going in either direction, it looks to me like 0 is going to be our identity. So our identity, and I'll say our identity is equal to 0. We have our identity. So now let's go back and look at inverses. I'll clear some of this away. And this is how we prove that something is a group. We just go piece by piece and figure it out. So, inverses should be such that when you do the operation on them, you recover the identity element, which is 0. It's going to be 0 for us here. So we need to know what 0's inverse is. 0 plus sign 0, or 0 plus sign something equals 0. Well, 0 is the identity element, so that's going to be 0. So the inverse of 0 here is going to be 0. That's easy. So inverses, 0 and 0 are inverses. Now let's look at 1. Where is it true that 1 plus sign something equals 0? Well, 1 plus sign 3 equals 0. 1 plus sign 3 equals 0. And 3 plus sign 1 equals 0. So we have in our new operation that 1 plus sign 3 equals 0, 3 plus sign 1 equals 0. They both give you the identity. So we have that they are inverses of each other. 1 and 3 are inverses of each other. And lastly, we have 2 plus sign 2. And we see that if we go 2, 2, 2 plus sign 2 equals 0. So 2 is its own inverse. So 2 comma 2 is its own inverse. And we see that all of our elements have inverses. So we are good with 4. I'll put my checks on the left side to make this a little easier to read. We're good with inverses. We're good with identity. Now let's check one of the cases of associativity. Let's see if it's associative. And let's spread this out a little bit. Bring this down. And let's see if we can prove associativity for one of the for a set of the elements. What's associativity? Associativity would tell us that, for example, 1 plus sign 3 plus sign 2 is the same thing as 1 plus sign 3 plus sign 2. So associativity tells us that when we move the parentheses around, we get the same element. And let's see if this is true. So first, I'll find 1 plus sign 3 because that's what's in parentheses. Well, 1 to 3 is 0. So we get 0 plus sign 2. And then 0 plus sign 2, I'll do that in purple. 0 to 2 is right here, which is 2. 0 to 2 is 2. So we get 2 on the left. And on the right, we have 3 plus sign 2. Let's find that. 3 plus sign 2 is right here. So that's 1. and 1 plus sine 1, 1 plus sine 1 equals 2. So we get that this equality is true. We have the associative property here, and thus we have a group. So that tells us that the clock with 4 hours forms a group under this new type of addition, under this new addition symbol. And that's how you prove that something's a group. You just go step by step using the definitions, and you see if the definitions apply to the group that you're applying them to. And that's all there is to it.